But here's a great example of where you would use the DCT. So this is a series that the DCT is the best test to use on this, and we're going to see series like this again. And it comes to how many times have we seen this and exploited this in calculus so far, right? The fact that sine and also cosine are bounded functions. So it says hint, the absolute value of sine of k is always less than or equal to 1 for all k, so it's bounded. So let's check that out. We're looking at the sum k goes from 1 to infinity, absolute value sine of k over k squared. Now to use the DCT, we need to have an inequality set up. 0 less than or equal to, or 0 is less than, and then we need two series in here. Now the hint kind of told us how to go with it. The hint told us that the sine of k is less than or equal to 1. So I've got the sine of k is less than or equal to 1. So I can build my series if I divide through everything by what? K squared. Whoops. All right. So now I can put the summations through. Right. Everyone cool with that? Now let's see if we can apply the direct comparison test. Do I know about this series here? What happens to this series and why? Does that converge or diverge? Okay, so we've got a difference of opinion there. What kind of series is it? Let's first, what species of series are we dealing with here? This one's not geometric. Geometric series, remember, are exponential functions. It's a p series. And what's the p in this case? What's the power p in the denominator? 2. And what's important about 2? That's right, it's greater than 1, which means this is going to converge. All right. So this is going to add up to a finite number. I don't know what number it is. I don't care what number it is. It adds up to a finite number. So what's going to happen to this one then? It's smaller than that. So it's also going to have to add up to a what? A finite number. So by the DCT, since the sum k goes from 1 to infinity of 1 over k squared converges, p series, p is 2 bigger than 1. The sum k goes from 1 to infinity of the absolute value of sine of k over k squares also converges. see how we're putting that logic together, folks? So hopefully that noise isn't too bad. This is week 3 of road construction here. I'm surprised they're doing it because I think we're in the middle of a thunderstorm, but okay. All right, well that's good. The noise canceling condenser mic is doing its work. All right, use the DCT to show the following series diverges, and we got a helpful hint. For k greater than or equal to 2, the natural log of k is less than k. So 1 over the natural log of k is bigger than 1 over k. All right, so we've got 1 over the natural log. Oops. So once again, we got to have these two series, and it's giving us a little hint here to get us started. So now I can put the series through. So you add up a bunch of zeros, you just get 0. We're adding this one up, and then we're adding this one up. All right, now, which of these do we know about? Well, this is what we're trying to figure out. What do we know about this dude? He's a famous one, right? He has a name. He's the what series? Remember the name of that one? If you don't remember the name of it, do you see what kind of series it is? So this is the harmonic series. And it's a P series with P equal to what? What's the power on that K? It's 1, which is less than or equal to 1, which means this diverges. And once again, we're adding up a bunch of positive numbers. The only way a bunch of positive numbers, when you add them up, will diverge is if this thing's going to blow up to infinity. And this sum is less than or equal to this sum, so what must happen to this sum here? If it goes to something bigger than or equal to infinity, then it itself must go to what? Yep. So by the DCT, since the series k goes from 1 to infinity of 1 over k diverges, so does the sum k go from 1 to infinity of 1 over the natural log of k. We know the smaller series blows up to infinity, and therefore we can conclude the bigger one has to go to infinity as well.